To the section 6.1 video lecture. For statistics, I am your instructor, Dr. Scott Spaniel. Welcome back. This is the first video for chapter 6. So we just finished talking about probability and the basics of it. And so what we're going to start talking about in these next couple sections are the idea of random variables and their distributions. So in chapter 6, we're going to talk about discrete random variables and give you a couple examples of discrete random distributions. And then in chapter 7, we're going to talk about continuous random variables, and we're going to talk about a couple of distributions that go along with that. And this is all leading up to using probability for inferential statistics, which is what we're going to do in chapter 7. So go ahead and take out, if you want to follow along in the note sheets, you can take out the chapter 6 note sheets, which can be found on Blackboard or my math lab. And we're going to start on the first page. So once this loads on my screen, we'll get started. So chapter 6 notes, like I said, there's 3 sections. So in section 1, we're going to talk about discrete random variables in general. In section 2, we're going to talk about the binomial probability distribution. And in section 3, we're going to talk about the Poisson distribution. So this first part is just kind of a couple definitions and then a reminder about the difference between discrete and continuous. A random variable is a numerical measure of the outcome of a probability experiment, so its value is determined by chance. Random variables are typically denoted using capital letters such as X. A discrete random variable has either a finite or countable number of values. The values of a discrete random variable can be plotted on a number line with space between points. A continuous random variable has infinitely many values. The values of a continuous random variable can be plotted on a line in an uninterrupted fashion. So we've talked about discrete and continuous variables back in chapter 1. These are the same idea here. We're just applying those two terms to the idea of random variables. So what I'd like us to do is look at some examples of random variables and decide whether they're discrete or continuous and what values they could have. So the time it takes a light bulb to burn out. So a light bulb can burn out in pretty much any decimal point of time. It's not something we count. In fact, it's something we measure. And so therefore, this is going to be continuous, right? Remember back to chapter 1, the way we could tell the difference between discrete and continuous was if we measure it, then it's continuous. And if it's countable, if it's something we count, then it's discrete. So this is continuous. And in this case, the time it takes could be really anything greater than or equal to 0 seconds, right? Because you could actually have a light bulb that's a dud and is burnt out before you even start. And that would have a time to burn out of 0 seconds. The next one is the weight of a T-bone steak. This is also continuous because we're measuring it. And this one, you could say the weight has to be greater than 0, right? Because if the weight of your T-bone steak is 0, then it doesn't exist. You don't have one. Okay. The next one is the number of free throw attempts before the first shot is made. The key word here is number, so it's something we're counting. So this is discrete. And the number of shots, number of attempts, in this case would be, we can't use inequality symbols like I was about to there because it's discrete. So it can't be any value greater than or equal to 0. It has to be an integer greater than or equal to 0. So we could write it like this, 0, 1. I'm not going to put that. 0, 1, 2, 3, and so on, right? It would just keep going. In a random sample of 20 people, the number with type A blood. Once again, you see the word number, which means we're counting it, so that's going to be discrete. So in this case, the number of people with type A blood, so let's just use a capital A for that, could be 0, 1, 2, 3, but there is a maximum here because we're only sampling 20 people. So that's 0, 1, 2, 3, all the way up to 20. Okay. So at this point, what I'd like you to do is pause the video and try the rest of these problems. So decide whether they're discrete or continuous and what values they could be. So the amount of rain in Seattle during April, that's something we measure, so that's continuous. And so that could be anywhere, so the rain could be anything greater than or equal to 0. The number of fish caught during a fishing tournament, once again, this word number is coming up, so that's discrete. And so that's going to be, number of fish would have to be 0, 1, 2, 3, so on. Number of customers arriving at bank between noon and 1 p.m. Once again, the word number, so that's discrete. I forgot a letter here. And that the number of customers could be anything from 0 and so on. It could keep going forever. We don't know what the maximum is, at least. And then the last one is continuous. The time required to download a file from the internet. It's time. We're measuring it. So therefore, the amount of time it takes the file to download for the internet would be f is greater than or equal to 0. So in this chapter, we're going to be looking at things that fall under the discrete heading, variables that fall under that discrete heading. A random probability, well, no, not random, sorry, a discrete nope, there, just probability distribution. The probability distribution of a discrete random variable x provides the possible values of the variable, random variable and their corresponding probabilities. A probability distribution can be in the form of a table, graph, or mathematical formula. So we've seen probability distributions previously, and they've always been as a table or a graph. And then this is one, the mathematical formula is one that we're going to use in section 6.2 and 6.3 with binomial probability distribution and the Poisson probability distribution. But the rules are the same for all of them. In order for P of x to denote the probability of a random variable x equals x, then the following have to be true to be a probability distribution. The sum of all the probabilities has to add up to 1, and each individual probability has to be between 0 and 1. So those are the same rules for just a regular probability distribution. So we're just reviewing that. So that was in chapter 5 that we mentioned that. A probability histogram is a histogram in which the horizontal axis corresponds to the value of the random variable, and the vertical axis represents the probability of each value of the random variable. These are almost identical to the idea of a relative frequency histogram. Okay, there's really almost no difference between the two. They're really the same thing. So this works the same as a relative frequency histogram. So the probability histogram that follows represents the number of rooms in rented housing units in 2005. Okay, so we've got our probability distribution. So we've got the number of rooms, and then we've got so those are the values of the random variable. These things down here, the number of rooms, and then we've got the probability for each. So what is the probability that a randomly selected rental unit has 5 rooms? Well, we just have to look at how tall the bar is, so 0.233. What is the probability that a randomly selected rental unit has 5 or 6 rooms? And so here's where we can start using some of our rules of probability, right, to go along with this. So the probability of 5 or 6 rooms really just means we want to add 5 and 6. So 0.233 plus 0.108. And so for that one, we're going to get 0.341 when we add those two together. What is the probability that a randomly selected rental unit has 7 or more rooms? And so that just means we just need to add anything that falls under the heading of 7 or more. So that's 0.037 plus 0.013 plus 0.005. And so when we add those together, we get 0.055. Okay, and so that's all there really is to that. It's just reading a histogram, right? Which we've practiced doing in previous chapters. So why don't you guys go ahead and pause the video for a second and try doing the same thing here. So what is the probability that randomly selected 50 to 54-year-old mother who had a live birth in 2005 has had her 4th live birth? So we just find the height of 4, so 0.128. What is the probability that a randomly selected 50 to 54-year-old mother who had a live birth in 2005 has had her 4th or 5th live birth? So same ideas on the last page. We just add 0.128 plus 0.060. So that's 0.188. And the last question here, what is the probability that a randomly selected 50 to 54-year-old mother who had a live birth in 2005 has had her 6th or more live birth? So we just add these three together. So 0.031 plus 0.022 plus 0.049. So 0.031 plus 0.022 plus 0.049 is 0.102. Okay, so that's one thing you should be able to do is read a probability distribution to answer questions. Okay, so now we said this is like a frequency distribution or a relative frequency distribution. So one of the things we can do with those is find their mean and standard deviation. So let's talk about how we could find the mean and the standard deviation. So the mean of a discrete random variable is given by the formula, the sum of all the p of x's times x, where x is the value of the random variable and p of x is the probability of observing that random variable. So suppose that an experiment is repeated n independent times and the value of the random variable x is recorded. As the number of repetitions of the experiment increases, the mean value of the n trial will approach mu sub x, the mean of the random variable x. In other words, let x sub 1 be the value of the random variable x after the first experiment, and x sub 2 be the value after the second, and so on. Then the mean is equal to x sub 1 plus x sub 2 plus x sub 3 plus dot 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 plus x sub n divided by n. The difference between x bar and mu sub x gets closer to 0 as n increases. Okay, so as if we were to take a sample of the results of these experiments, we should get closer and closer to the mean of the random variable x as we go along. Okay. Because the mean of the random variable represents what we would expect to happen in the long run, it is also called the expected value. And we write it like this, capital E of x. The standard deviation of the discrete random variable is given by the formula the square root of the sum of all x minus mu sub x squared times p of x, where x is the value of the random variable and mu sub x is the mean of the random variable and p of x is the probability of observing the random variable. Okay. So let's just try using some of this idea. So verify that the first thing they want us to do is verify that this is a discrete probability distribution. So if we wanted to here, we could use are, we could use Google Docs to help us do this. So I want to see, I can't remember if I have a problem set up for this one. Sheet already made for this one. So let's bring up our Google Sheets. And see if I have one for 6.1. Oh no, that's for another problem coming up. But let's go ahead and just add another sheet here, and we can use Google Sheets to show how to do some of this calculation. So I'm just going to add in another sheet to our problem set here. And call it 6.1 problem. Let's actually call this problem 1 because it's going to come first. I'll fix that later. Okay, so let's go ahead and just take the data from our problem and insert it in here. So our data was we had our x values, and then you've got your p of x values, and our x values were 0, 1, 2, 3, 4, 5, and these were the number of hits in a game by Ichiro Suzuki during the 2004 baseball season when he set a record for the most hits in a season at 262. Okay. And so it says the problem wants us to verify that this is a discrete probability distribution. So there's a couple things we need to do there, right? One is we need to make sure that the value of each probability is between 0 and 1, which you can see here, these all are. And then the other thing we need to do is we need to make sure the sum is equal to 1. So if I just do, we've used the sum command before, right? If I just tell it sum of B2 to B7, we'll add those all up, and we get 1, so that's great, okay? So yes, it is a discrete random. So yes, because 0 is less than or equal to p of x is less than or equal to 1, and the sum of all the p of x's is equal to 1. Then it says draw a probability histogram, okay? So we can do that. If you just select all your data, and choose, go to create chart, right? Insert chart. This hopefully will make us a nice little histogram. It made us a line chart, which isn't really what we want, but we can make it a histogram. It's making it more of a bar chart. So let's see if we can find histogram in here, because we know that exists. Yeah, let's do a histogram. Oh. And then one of the things you're going to have to do if you do a histogram like this is I'm going to have to customize it because it's using the wrong bucket size. And what I want the bucket size to actually be is 1. Oh, and it's got them reversed. Okay, so let's see. Okay, so I had to switch columns. Sorry, this is... Okay. For whatever reason, this is not working well. So let's delete this. And let's try one more time. It works good as a line chart, so the line chart looks good. I mean, here are the right probabilities, but it should be making me a histogram, which is not doing. It's not a big deal. It's supposed to be a histogram, but if you just use a bar chart, it'll give you all the same ideas. So you can see there's our probability histogram, kind of. And if we want it, we could try and do this in class calc. Let's see what happens if we try to draw this in class calc. I'm going to guess it's not going to work great, but we can go ahead and give it a good old try and see what happens. Oh, but didn't like that. And for some reason, the wrong thing's copied. Anyway, let's just leave it alone. Okay. So there's our histogram. And it says draw a probability. Compute the mean of the random variable. So we can make it do that. So we're not just going to be able to use the normal mean, but we can do it by using some of the formulas we've used before. So the formula tells me that I need to multiply the value times the probability. So that's my column 1 times my column 2, and then add those all together. So to do that, I'm just going to do equals A2 times B2, right? And then I'm just going to hold here and pull down, and it should do all of those for me. And then if I bring over this one to the right, whoops. And then I want to add those all together. So if I bring this over here to the right, it should add those all together, and there's my mean. So the mean is 1.6273. And we got that by using the formula, multiplying x times p of x, and then adding them all together. Okay. Then it says compute the standard deviation. So once again, we want to use the formula. So if we go back to the formula here, it says we want to take the sum of all the x minus mu sub x's squared, and then we want to multiply that by p of x. Okay. So what I want to do is I need to use another formula idea here again. Okay, so I'm going to do, in this column, I'm going to do each one of these because they're going to get added together, and then we're going to take the square root of them. So what I'm going to do in this formula is I'm going to write out what the formula says, which it says take x, which is A1, minus mu sub x, which is C8, and I want it to not move C8, so I'm going to put a little dollar sign in the middle, so that's going to make it not change C8 when I pull it down. And I want to square that, so caret 2. And then I want to multiply that by the p of x. And whoops, I put the wrong A2, sorry. X value is A2. And then I want to multiply that by the p of x, which is, so times B2. Okay, and if I pull down, it should do that for all of them. Okay. And now we want to sum those, so I can just pull over the sum formula. And then I want to take the square root of that. So equals square root of D8, the one right above it. And there we go. So that should be the standard deviation. So 1.1785. Okay, so this is a little clunky because these aren't built in here, so I'm just having to use the formulas. And now they have a couple questions with this sheet. So they say, what's the probability that a randomly selected game each year got 2 hits? Well, that's simply from the chart or from our chart here, which is we go to 2 hits. And where x is 2, p says 0.2857. And then what is the probability that a randomly selected game each year got more than 1 hit? And so then we just have to add up all the ones that are more than 1 hit. So 0.2857. plus 0.1491 plus 0.0373 plus 0.0248. And so that's 0.4969. So in about half the games, he got at least 2 hits. Okay, and so that's the idea of how you can find the mean and the standard deviation. So there's no really good shortcut with the way we're doing this, but that is probably the best way to do it, is using Google Sheets. Okay. Okay, so at this point, I don't have this data currently entered in the sheet, but I'll add it here in a second while you guys work on this. Why don't you guys go ahead and take, pause the video for a second, bring up problem number 6.1, problem number 2 in your Google Sheets, and then we'll go ahead and try this together. So this is going to be 6.1 problem 2. And so you can try this in Google Sheets, and then once you're done trying it, unpause the video, and we'll go through these together. Okay, so now that we've done all that, we can start by verifying that this is a probability distribution. All the values are between 0 and 1, so now we just need to check the sum. So that's B2 to sum of B2 to B16. And we get a sum of 1, so that's good. And then we're going to do the mean over here. So we're going to do x times P of x. Okay, so we just do it for the first column. So that's A2 times B2. And then we can highlight that, put our box over that, grab the little box in the right-hand corner and pull down. And we'll do the rest of them. And then to find the mean, we just add those together. So we bring over our sum. And so the mean is 4.875. So in this case, that's what that means is we would expect that during lunch at this Wendy's that they'd have about 4.875 cars in line at any given time. Okay, on average. That's the expected value of that. And then if we want to do the standard deviation, we do the square root. And this one's a little harder to write out, but we do the square root down at the bottom. Well, actually, so what we want here is we want x minus mu squared times P of x. Okay, is what's going in this column. So that's A2, whoops, equals, don't forget the equals, else it won't do it, A2 minus our mean, which is in C17, so C $17, close parentheses, squared, times P of x, which is in B2. And there we go. And then we want the first thing to change, but we don't want the second one. So notice I didn't show this in the last one, but if you watch what's happening up here, as I scroll down, the first letter number combination is going to change. The last letter number combination is going to change, but this middle one's not going to. And that's what that $sign does. And then we want the sum of all those. So bring over our sum, and then we want the square root of that. So down here we can type square root, SQRT, parenthesis, and then the cell we want the square root of, which is D17. The one right above it. So there's our square root. Okay, so we've got the mean is 4.875. The standard deviation is 2.246. Once the variance, sorry, but so one other thing to get the variance, this number right here is the variance, right? It's the square of the standard deviation, so 5.043, right? It's the square of that, so if this is the square root, then the number we took the square root of it is the variance. And then what's the probability that 8 people are waiting in line? Well, that's just right here. So that's 0.063. And then what's the probability of 10 or more people? So we just need to add these together. And if you wanted to, you could use Google Sheets to do that too. I can do a sum, and then I just tell it which columns I want, which is 10 or more, right? So I'm going to highlight 10 or more, close parenthesis, and there's my answer, 0.127. Okay, and so that's the idea and how you can use Google Sheets to do these. Okay, so now let's go into to finish off this section. The last thing we need to talk about is more about this idea of expected value. So, expected value is the idea of using this mean to figure out what we expect to have happen. So some standardized tests, such as the SAT test, and I don't think they do this anymore, but they used to, at the very least, incorporate a penalty for wrong answers. For example, a multiple choice question with 5 possible answers will have 1 point awarded for a correct answer and 1/4 of a point deducted for an incorrect answer. Questions left blank are worth 0 points. Find the expected value of the points received for a multiple choice question with 5 possible answers when a student guesses. Okay. So what you want to do when you're doing problems like this is, what are the outcomes? What is the value of each outcome? And what is the probability of each outcome? Okay, right? This is, the value is X. And then we've got the probability. So in this case, the outcomes are you get it correct, you get it wrong, or you skip it. Okay? And according to the problem, it says that if I get it correct, I get a point. If I get it wrong, I get a 1/4 of a point deducted. And if I skip it, I get 0 points. Okay? So what is the probability of getting the question correct if it's a 5 question multiple choice with 5 possible answers? What's the probability of getting it correct? Well, that would be 1 in 5. What's the probability of getting it wrong if I answer it? Well, that's 4 out of 5. And what's the probability of getting it if I skip it? Well, that's just 0, because if you skip it, you have no chance of getting it right. So now we find the mean, right? So what we do to do expected value is we multiply these together and then we add them up. Okay, so this would be 1 times 1/5 is 1/5. Negative 1/4 times 4/5 is negative 1/5. 0 times 0 is 0. And when I add those all together, I get 0. And so the idea here is if you guessed on every question on the SAT, you would get 0 points. And that is why they do it this way. They don't want you to guess. They want you to know the answer or skip it. And the reason they did that is they made a wrong answer have the same value as a guess have the same value as skipping. And they do that by taking off points when you get a question wrong. And that's the idea behind expected value. Another example where we use expected value a lot is with gambling, because it's a case where we know the probabilities, we know the values of winning, and we know what it costs to play. So in the Cash 5 lottery in Connecticut, a player pays $1 for a single ticket with 5 numbers. 5 balls numbered 1 to 35 are randomly chosen from a bin without replacement. If all 5 numbers on a player's ticket match the 5 chosen, the player wins $10,000. The probability of this occurring is 1 out of 324,632. If 4 numbers match, the player wins $300. This occurs with a probability of 1 in 2,164. And if 3 numbers match, the player wins $10. This occurs with a probability of 1 in 75. Compute and interpret expected value of the game from the player's point of view. Okay, so what we can do is we can set it up the same way. So outcome, value, okay, probability. So in this case, the outcomes they give us are you get 5 correct, 4 correct, or 3 correct. The value of getting 4 correct, 5 correct is $100,000. The value of getting 4 correct is $300, and the value of getting 3 correct is $10. And then they give us the probabilities. 1 out of 324,632, 1 out of 2,164, and 1 out of 75. And so what we can do is we can do this problem, and I like to ignore this number for now. So what I want to know for now is what is the expected value of a win? So what is E of a win? So E of a win, all you have to do is figure out the mean, the expected value of the 3 winning scenarios. And I went ahead before class and put this one in a sheet. Okay, which I'm going to change the name to say problem 3. Okay, so this is 6.1 problem 3. So I went ahead and did this, and I went ahead and put the probabilities in. Notice that if you look up here, I have the actual written out, but I went ahead and did the divisions just to make things a little easier. And so what I can do is I can do exactly what we've done with the previous ones. What I want to do is I want to multiply the value times the probability. So A2 times B2. And then I want to, okay, and then I want to bring those down. Something's not right. Let's get rid of the formatting. I added that. Okay. Actually, okay, so I made them all dollars. Okay, so there's the formatting. So then we add these together, and that's my expected value. So the expected value of a win. So if you were to win, how much you would expect to win every time you played this game. So then sum of these 3, okay, is 58 cents. Okay, so we would expect on average to win 58 cents every time we played. Now the problem with that is that is not how much the value of the game from the player's point of view, because what does the player still have to do? Well, every time they play, they have to pay $1. So if on average they win 58 cents, but they had to pay $1, they're actually losing money. So we have to subtract $1, and their actual value is negative 42 cents. Right? Because they, on average, are going to win 58 cents, but if you pay $1 to play, you're actually losing money each time, right? If every time you pay $1, you get 58 cents back, you're losing $42 each time. And one of the things they're going to ask you to do, maybe on one of the homework problems, is, well, what if we wanted, how much would this top prize need to be in order to break even? Like have the expected value be breaking even. So every time you paid $1 and you, on average, would get $1 back, so you wouldn't lose any money. And so the easiest way to do that is to simply, when I have it set up like this, I should just be able to change this column. So let's add an extra 0 in here. Let's make it $1 million for the win. And notice what that did. That brought that way up. So now I'm way over. Okay, so now I'm definitely winning money. So let's take this back down to 500,000. Okay, so now it's $1.81. So now I'd be making 81 cents. So let's make it 200,000. Okay, so 200,000 I'd still be losing. So let's make it 250,000. And there I'm at $1.04. So somewhere between $200,000 and $250,000 is the break-even point for this game, if that prize. But this is actually the way that lotteries make money, right? When a lot of people play this lottery, on average, they're going to make 42 cents off of everybody who plays. Even if they give out the jackpot, they're still going to make 42 cents on average from everybody who plays, so therefore, they're making money, even though people are winning. And this is how casinos work, right? This is how they all make money. So that's the idea there. So when I do these problems, like to, for the most part, ignore the cost until the end. So I find the value of winning and then throw that in. So what I want to do to finish off today is just have you guys try these last 2 problems on page 9. Pause the video. When you're done with them, we'll go through them together, and then that'll be it for today. Okay, so now you've had a chance to try these, let's go through these. So a life insurance company sells a $250,000 one-year term life insurance policy to a 20-year-old male for $350. According to the National Vital Statistics Report, the probability that a male survives the year is 0.998734. Compute and interpret the expected value of this policy to the insurance company. Okay, so if for the insurance company, there are 2 outcomes, right? Either the person lives or they die. Okay. The value to the insurance company, if they live, is nothing happens, right? They don't have to pay out anything. But if the person were to die, they have to pay out $250,000. So that's a negative $250,000. The probability of the person living is 0.998734, and the probability of them dying is 1 minus 0.998734, right? Because those are the only two possible outcomes. Okay, if we multiply these together, so this is to do the expected payout. If we multiply these together and add 0 times 9.48 is 0. So if we multiply those together, so x times p of x is what I'm putting in this column. And then if I multiply the other one, negative 250,000 times 1 minus 0.9987734 is negative $316.50. So on average, they're paying out $316.50. However, that's where this part comes in. For every insurance policy, they charge $350. So their expected profit is the sum of those two, the difference between these two numbers, which is $33.50. So on average, on an insurance policy to a 20-year-old male, they're making $33.50. Okay. So that's the idea for that one. And then for this one, Sean and Maddie purchase a foreclosed property for $50,000 and spend an additional $27,000 fixing it up the property. They feel that they can resell the property for $120,000 with a probability of 0.15, $100,000 with a probability of 0.45, $80,000 with a probability of 0.25, and $60,000 with a probability of 0.15. Compute and interpret the expected profit for reselling the property. So we've got the value, which is the sale price. So 120,000, 100,000, 80,000, and 60,000. And then we've got the probability of each of those, which are 0.15, 0.45, 0.25, and 0.15. So we multiply those together and add. So 120 times 0.15. And you could do this in Google Sheets. I'm doing it on a handheld in my calculator app right now, but you could use so these are the sale price. I'm just going to add that in because I think that'll be important to remember. Okay? And so if you add these together, $1,322, you get $92,000. And so that's this is their expected sale price, which is not their expected profit, right? Because they had expensive. So you need to subtract $50,000 for the cost of the property, which gets us down to $42,000, and then you need to subtract how much it cost them to fix it up, which gets us down to $15,000. So their expected profit is $15,000. Okay. And so that's the idea of how these expected value problems work. So that's it for today's video lecture. I'll see you next time when we're going to talk about binomial probability distribution. As always, if you have any questions, feel free to ask them in class or send me an email or a remind message, and I'll get back to you as soon as possible.